Hi ladies, we are going to jump into our very last new bit of material for calculus. Crazy times. So it is all about solving differential equations, and again, they're going to be separable. And these are specific applications related to exponential growth and decay, even though they're kind of hidden. So a lot of times when we're given we're given differential equations, they're related to things that are in proportion to another. So a lot of times that they'll say that the rate of change is proportionate to the amount. And that makes a little bit of sense, and we'll talk about why in our second example. But in our first example, we are just going to go ahead and translate exactly what they tell us, and then go ahead and solve. We are going to be solving our differential equation, and it will be a specific solution because of these ordered pairs they give us at the end. So let's just translate what we've got. So the rate of change of y, well, that right there, rate of change of y is just dy over normally dx, but a lot of times today we're going to be using t for our independent variable. So dy dt is directly proportional to y. We'll think way back to when we first learned direct variation. Instead of saying direct variation, a lot of times they could say directly proportional. So often it was directly proportional to x or directly related to x, but this time it's directly related to y. Now our goal is going to be to find out what that k value is, because that's our constant of variation, and then we'll find out what that is in addition to another constant that we'll get here in a minute. So if we have dy dt equaling some constant times our value of y, we can solve this by separating, right? So we are going to multiply both sides by the differential dt to get it to cancel. So we'll move our t's to the right, and we'll move our y's to the left. So we'll multiply by the reciprocal. And we do that because 1 over y dy, it's going to be a lot easier to take the antiderivative of that here in just a minute. And then the right-hand side, we just have k dt with respect to t. So as I said, we take the integral of both sides, the antiderivative. The antiderivative of 1 over y with respect to y is the natural log of the absolute value of y, and technically plus the constant, but we'll handle that on the other side. On the right-hand side, the antiderivative of a constant with respect to t is just going to be k times t, and then we'll throw on that plus c at the end. Now remember, yesterday we put a lot of our ordered pairs in at this stage before we solve for y. Today it's actually going to be beneficial to solve for y first. So to get rid of a natural log, I would often say that we would log loop it, right? And that's exactly what we'll do. So log base e is going to change e as it's going to make e the base of our exponent. So e to the kt plus c is going to be equal to the absolute value of y. Now, just like yesterday, if we have e to a sum, you can split that up and say, well, that's like e to the kt times e to the c, because our exponent rules can also work in reverse. The reason we do that is because e to the c, e to some constant, is just going to be some other constant, which we don't really care. So yes, we call it the same c every time, which is not technically true, but that's really okay for us. And that is equal to the absolute value of y. Now, again, yesterday we talked about if you've got positive values of y, you don't need the plus and minus, or I guess you don't need the absolute values. So from here we will get to chuck those absolute value bars out the window. So y is equal to c times e to the kt. And notice, all of a sudden, we came up with our exponential growth function, right? Remember, we often use this for continuously compounded interest, and we call it PERT. But notice, it's the exact same function. So this is where we get it. This is where it comes from. Kind of cool, full circle. So now that we have our general function, we are going to go ahead and find both of those constants, right? We need to find c and k. And we'll do it by just plugging both of these in separately. If you are ever given an independent variable of 0, plug that in first, plug in that ordered pair, and we do that because we'll have 8 equals c times e to the 0th. Well, what's e to the 0th? Just 1. So that means that 8 is going to be our c value. So now our equation reads y equals 8 e to the kt, And now as we plug in that second ordered pair, we are only going to be solving for k. So we have 10 equaling 8e to the k times 5, or 5k. Our goal is to solve for k. Divide both sides by 8 and reduce that fraction. So 5/4 equals e to the 5k. And we'll log loop from here. So the natural log of 5/4 will get us 5k. So that means that k is going to be equal to, we're going to divide both sides by 5 or multiply by 1/5 times the natural log, of 5/4. Now, don't get lost about what we were trying to do. Our job was to solve the differential equation. Remember, your solutions to those are equations. So this was just finding out our second constant. So our final answer is going to be y equals 8e to the, well, that's our fun k value, 1/5 times the natural log of 5/4 times t. And there is our final answer. Now, the reason this is super important and super pertinent is because this is exactly what's happening with COVID-19. So in example 2, the rate at which the number of confirmed cases increases is proportional to the number of cases. That makes sense, right? If it's a communicable virus, then the more people that have it, the more people they're going to spread it to. So it makes sense that if there are more people, then it's going to be spreading faster. There are more people that have it, it's going to be spreading faster. So the rate at which the number of cases increases, well, let's call the number of cases P. So then the rate at which it increases, or the rate at which it changes, is going to be directly proportional to the number of confirmed cases you have. This is the exact same equation we just had from up above, just with different variables. And then from the CDC, we found that on March 10th, there were 937 confirmed cases. And then one day later, there were 1,215 confirmed cases. So there was a pretty common ratio of how much it increased each day. And we'll find out exactly what that is here in a minute. But this was pretty typical, which is why I chose those 2 particular days. That was also the night before, or I guess the change into when they called off school for us. So this might be something that they were considering when they called school. So based on this information, how many confirmed cases could have been expected on March 29th? Know that I chose that date. Yes, it was a couple days ago, but that was the one, the most recent information that I could get on their website. So let's talk about what sorts of predictions that we can use to make, or that we can make using the model that we'll find here in a minute, and also how accurate that prediction may be. So we have dp dt equaling k times p. And even though we just did this and it's the exact same process, we're going to go through it for the sake of, well, yeah, our goal is to actually solve differential equations. So we separate our variables, and we're going to multiply by 1 over p as well. Oops, that's not a p. So we have 1 over, well, you get the idea. 1 over p dp equals k dt. And we integrate both sides. And just like before, we get the natural log of the absolute value of p. Now remember that p stood for the population that has a confirmed case of the coronavirus. We don't need it in absolute values because it will always be positive, right? You can't have a negative population. And that's going to be equal to kt, not dt, oh boy, plus c, there we go. And we will exponentiate both sides, or we will log loop it, right? So we have e to the kt times e to the c. Well, remember that e to the c can just become some brand new constant, magically, and that's going to be equal to the population. Now, we take a look at the information they gave us. So they said that on March 10th, there were 937 cases, and the 11th, there were 1,215. They give us 2 ordered pairs, and you can let your x, or your t in this case, really kind of stand for whatever would be most beneficial to you. So if we want to let let t equal 0 correspond to March 10th, then we can use the ordered pair of 0, 937, and right away we know what our c value is, right? Remember that just like in the last problem, when we end up plugging in that ordered pair, as we solve for our 2 unknowns, we just find out, oh yeah, c, that starting value is going to be your starting value, right? And then next we have on the 11th. So that's going to be 1 day later, assuming T is time in days. 1 day later, there was 1,215 confirmed cases. So we will now use that ordered pair to plug in and solve for K. So P equals, let's see, we just said C was 937 times e to the K times 1. So then, oops, sorry, not even P, because we should be plugging in our second ordered pair as well. So we plug in 1215 for that P value, that dependent variable. And as we solve for K, we first want to divide both sides by 937. And so as you're looking at the daily increase, you are really looking at the ratio, the percentage increase, I guess you could say. You're looking at the ratio of the number of cases from day 2 to day 1, day 3 to day 2, right? And then that ratio ends up being often about 1.3 is what we're typically seeing. In this particular day-to-day, it ends up giving us, what was it? I guess I didn't even bother writing it down, but it is about 1.3. So if we keep that as a fraction right now, 1215 over 937, that's equaling e to the k. So to get k by itself, all we have to do is log loop. So k is going to be equal to the natural log of that 1215 over 937. And we can get a decimal approximation. I went ahead and kept all the decimals that I could though. So k is about 0.25981607. And so now we are going to be able to determine how many confirmed cases we would have expected on March 29th. So what we have to do is we have to figure out what our final equation was. I guess start there. So P is going to equal 937 e to the, oh boy, fun decimal, 0.25981607 t. And then from here, we need to figure out what we're going to be plugging in for t if we want to know what's happening on March 29th. Well, remember we let t equal 0 represent March 10th, so we need to subtract. So that is really day 19 based on how we were keeping track. So we have P equals 937e to that 259.81607. And because it's exponential growth, those decimals really do serve a purpose. So I always try to keep a ton when I'm doing this just to be safe. And then from here, we can just plug it directly into our calculator. We find that we should have expected about 130,508, and I rounded to the nearest whole number, obviously, confirmed cases on the 29th. Now, they ended up finding exactly 140,904 confirmed cases, according to the CDC's website. So a relatively accurate model, given the fact that it's exponential growth, and it could have been a lot farther off than that. Still not, overly joyous news, but kind of cool that the math ends up